If you have a small signal, you cannot feed it into the microcontroller right away. You need to amplify it first. And for that, you need some sort of an amplifier. However, traditional amplifier circuits can get quite complicated with a chip surrounded by resistors or even possibly trimmer pots. So here I'm going to present a fairly simple circuit that can amplify the signal 1, 2, 4, 5, 8, 10, 16 or 32 times, and it's a through-hole chip, so you don't need any special soldering skills for this. The chip I'm going to talk about is MCP6S21, which is a single-ended, rail-to-rail, low-gain, programmable gain amplifier, and it uses a serial peripheral interface, SPI, so I'm going to connect it to a Raspberry Pi Pico that will be used to set the gain between 1 and 32. So here how the circuit looks like. I have 3.3 volts coming from Raspberry Pi Pico. The clock signal goes to GPIO 6, input goes to GPIO 7, and channel select goes to GPIO 16. Also, I need to supply a ground. Here is how it looks like. Now, on the left side, I have the analog inputs and outputs. I have the ground, and the reference voltage is also connected to the ground. I have the arbitrary wave generator going to 4.7K resistor and adjustable capacitor before going into the input. There are two reasons for that. First, I want to protect the input from accidental voltage, and this 4.7K resistor will protect it up to plus minus 10 volts. Also, the resistor and the capacitor form a low-pass filter, so I can filter out any high-frequency noise that I don't want, because that is going to get amplified a lot inside the amplifier. For the output, I immediately connect it to 100 ohm resistor, and then only then feed it to channel A of the oscilloscope. The reason for that is this operational amplifier is fairly sensitive to the capacitance in its output. So I want to connect a resistor first, and then do not worry about any consequences of such sensitivity to capacitance. For example, if you are not careful, then this circuit can easily oscillate, and you are not going to get a very good result, just a lot of hash instead of the amplified signal. This is also a reason why I'm not making this prototype on a breadboard, because breadboard adds all kinds of stray capacitance inside. So instead, I'm soldering it right in, and here you can see how this looks like. So here I have the chip and all the components around it. Here is the adjustable capacitor, and let's take a look at another angle. So here is the output resistor, here is the input resistor, and the oscilloscope probes and output of the arbitrary wave generator going inside the input. These are the connections going to Raspberry Pi Pico. So this is the setup. It's not perfect. You can get much better results by using a specially designed printed circuit board, but for now that might just work for you. So let's proceed to the tests. In Picoscope, I have an arbitrary wave generator set up to generate a sine wave 100 kHz with amplitude 60 millivolts and offset 140 millivolts. This is what you can see on the blue trace. Now, when I go to the terminal and execute the following Python code on Raspberry Pi Pico and then set gain to equal to 1, I get the red trace on the output. We can see that it matches the blue trace fairly well. It does add some noise. Now let's set the gain to 2 and see what happens. So now we see that the amplitude increased about 2 times, and we will go further. We will switch the voltage scale to plus minus 5 volts and set gain to 4, then 5, then 8, then 16. So here we see that we amplified the original signal 16 times. There is some noise on the line, high frequency noise, and we can control that using the adjustable capacitor that I included on the board. So let me just change the capacitance value, and we can smooth out this sine wave, but of course we are going to reduce the bandwidth. Now what happens if we go to gain 32? We get some clipping because the amplitude is so high that it goes beyond the 3.3 volts, which is the power supply. So at that point it gets clipped. The bottom is still kind of half sine wave, though there is quite a bit of noise on the line. So in general, this amplification works as desired, though of course you don't want to amplify more than necessary. For my purposes, for example, I have this signal as a square wave, and after I do the amplification, I get a signal in between 1 volt and 3 volts that I can now direct to the microcontroller to input it as a digital signal.